Good day, ma'am. We are the Group 4. I am Richard Buhay, and today we will be presenting our Project 1, which is the AHI-Count 7-segment display simulation using the Logisim software. For this course, Logic Circuits and Design Laboratory. So let me start with the discussion of the problem. So we are required to design a system using an adder and decoder which outputs the severity of sleep disorder as shown in the table with respect to the count of sleep disorder, also known as the AHI-count occurrence. Two sensor values represented by input pins increment the counter whenever sensors 1 and sensor 2 values are greater than or equal to the threshold values. So here is the set of data that is assigned to our group. It says here, if the AHI-count is within 0 to 10, the display will have an output of 0. If the AHI-count is within 11 to 15, then the output will display 1. If the AHI-count, on the other hand, is within 16 to 20, then the output will display 2. If the AHI-count is within 21 to 27, then the output will display 3. And last condition is that if the AHI-count is within 28 to 32, then the output will display a value of 4. So in order for us to better understand this problem, so let me discuss first about the 7-segment display. So here is the illustration of the 7-segment display LED, which can be found in the Logisim software. So it represents like a number 8, wherein it consists of 7 distinct segments, which are denoted by letters A up until letter G. That's why there are 7 in all. So each of these segments will either light up or not, depending on the required output, which will be displayed by the LED. So for instance, if the output is 0, the only segments that have a high signal are A, B, C, D, E, and F, while G has a low signal in which it will not light up in order for the output to display 0. For 1, the only segments that have a high signal are B and C in order to form an output of 1. So the next one is 2. The only high signals are segments A, B, G, E, and P, while C and F are low signal, so that an output of 2 will be obtained by the LED. As for 3, the only segments that are high signal are A, B, G, C, and D. For 4, here is the only segments that have a high signal are segments F, G, B, and C. So for 5, the only segments that have a high signal are A, F, G, C, and D. So for 6, the only segments that have a high signal are all of them except segment B. In short, B is the only low signal in order to create an output of 6. So for 7, the only segments that have a high signal are A, B, and C. As for 8, all of all of the segments have a high signal. And lastly, output 9, the only segment that has a low signal is segment E, while the others have a high signal in order to form the output of 9. So here is the truth table that we created in order to analyze the inputs and the outputs for our problem. So let me go back first for a while for the problem. So here it is. So the given I counts are only from 0 to 32. That's why our group decided to create a 5-bit input which contains 32 different results. 32 is obtained by raising 5 from 2, or 2 raised to 5. That's why we arrived at 32 different inputs for the 5-bit input. So going back to the truth table, so we created 32 different inputs from 0 to 31. So let me go back for a while. So it says here, so let's go back. An output of 0 will be displayed if the AHI count is within 0 to 10. So for the truth table, the binary form of all the AHI counts are obtained, which will be essential to determine which input it is, because different AHI counts have different inputs as defined, which depends on their binary value. So, like what I said earlier, if the AHI count is within 0 to 10, an output will be 0. But based on the 7-segment display, an output is 0 if the only high signals are segments A, B, C, D, E, and F. And the only low signal is G, which is illustrated in this LED. So the only 0 is G because it has a low signal, while other segments have high signal or have a display of 1. Next is, so next condition, if the AHI count is within 11 to 15, then the output will display a value of 1. So going back here, an output display of 1 is where it has B and C as its high signals based on the convention in this figure. That's why segments B and C in this condition are the only ones that have a value of 1 for this condition, for the AHI count within 11 to 15. Then moving on to the third condition, the third condition, so going back on the problem, if the AHI count is within 16 to 20, then the output will display a 2. So 2 is where the only high signals are segments A, B, G, E, and B. So those segments, this is A, this is B, this is G, this is E, and this is D. So they're the only ones that have a high signal for this condition in order to display 2 as the output. So moving on to the next condition, so let's go back. So let's refer to this problem. If the AHI count is within 21 to 27, then the output will have a display of 3. As what I explained earlier, an output of 3 is where the only segments that have a high signal are A, B, G, C, and D in order to form 3 as the output. So here is A, B, G, E, and D in order to form an output of 3. Okay, so for the last one, if the AHI count is within 28 to 32, therefore the output will be 4. So the output is 4 if the only segments that have a high signal are F, G, B, and C. So in this table, this is F, this is G, this is B, and this is C. They have a value of 1 because they are high signal. They have a high signal in order to display an output of 4. So the next is the K mapping. So each of the outputs are analyzed in order to obtain a logic function by the use of K-maps. Specifically, the sum of products. So 7 different K-maps were created. Specifically, 5 variable K-maps since we are dealing here with 5 inputs. Yeah, and we created 7 in all because there are 7 outputs that are needed in order for us to come up with the desired 7-segment display for the output signal. So let us go to the K-map for output A. So this column from 0 up until down to 31 is the output for A. So here is the K-map that is created in order to analyze output A. So where is my pen? Yeah. So the grouping that we did in order to analyze is first is this one. We group these 8 ones on the first K-map. And then the second group will be this one. This one. Wait, let me use another color. So this one, yellow group, and this one, the 4 of them. And the last group is the 2 of them. This one. Wait. This one and this one. So moving on to this K-map where A is equal to 1. So here is the grouping that I made. The first one is this one, the 8 ones. And the second one is, let me use a different color. This one and this one. So for the logic function, so here is so first one is the red group wherein A is equal to 0, B is unchanged, which is 0, and then C, D, and E literals are changed. Therefore, we are left here with A prime multiplied by B prime. And the next one is the yellow group wherein A is equal to 0, B changed from 0 to 1, therefore cancelled, and then C is unchanged, it is just 0, and then D is unchanged, it has a value of 0, and the literal E changed from 0 to 1. Therefore, we are left with A prime, C prime, and D prime. And lastly is the orange group, wherein A is 0, B changed from 0 to 1, C is unchanged, which is 0, D is 1, and E is 0. Therefore, the logic function will become A prime, C prime, D, and E prime. So that is the logic function for this part, wherein the literal A is equal to 0. So moving on to this second part, wherein literal A is constant, which is 1. So focusing on the green group, so green group, so A is constant at 1 or is unchanged, B is unchanged also, which is 0, but literal C changed from 0 to 1, as well as the literals D and E. Therefore, we are left by A and B prime. The next group is the green group, blue group rather. So A is unchanged at 1, B changes from 0 to 1, therefore cancelled. C is unchanged, it is just 0, therefore it will become C prime, and then literals D and E changed from 0 to 1, and vice versa. Therefore, we are left by A and C prime. So combining these two obtained functions, so adding them together, we'll get the logic function for output A, which is simply the sum of these two functions. But based on what we obtained here, we can simplify the given expression. So for instance, we have here A prime and B prime as well as A and B prime. Factoring out B prime, we will obtain B prime multiplied by A prime or A. But there is a property which states that A prime, which is ORed with A, will have a value of 1. Therefore, we are left with B prime. Therefore, this is the logic function. However, this function can still be simplified by applying the simplification theorem. Therefore, we are left with B prime or C prime D prime or C prime E prime or A C prime, which is the logic function for the output A. So moving on to output B. So let me clear first. So for output B, so here is the K-map that I made for output B. So let us check again the truth table for output B. So this column is for the output B. So based on the truth table, all cells under column B have a value of 1. Therefore, for the K-map, all of those will contain, all cells will have a value of 1. So for the logic function for output B, so the grouping will just, where's my pen? For A is equal to 0, so the grouping will be the entire K-map, as well as if A is equal to 1, the grouping will become this one, the entire K-map. So for the blue group, where A is equal to 0, since all of its cells contain a value of 1, therefore the literals B, C, D, and E will cancel. We are left with A is equal to 0, which is A prime in SOP. And then, for the second part of this K-map, wherein A is equal to 1, since, again, all of the cells are 1, literals B, C, D, and E will all cancel out. Therefore, we are left here with A is equal to 1, or simply A, which is in SOP. Therefore, in order for us to determine the expression for output B, we will simply combine the two expressions. So it will become A prime, which is ORed with A. So applying here the property, it will just become 1. Because a literal which is ORed with its complement will always have a value of 1. So this is just 1 for the output B. So moving on to the next one. So let me clear this. For output C, so here is the K-map that we did for output C. So the grouping that I made was this one. Okay, so for this part, A is equal to 0, the grouping is like this. The entire part of the K-map. If A is equal to 1, the grouping is this one. Here's the second group. The third group is this one. Well, the last group is, let me change the color. So this one. So for the first group, so since in this part, all of the cells are 1, therefore, literals B, C, D, and E will all cancel. We are left here with A is equal to 0, which corresponds to A prime. So this is A prime when A is equal to 0. And then in this part, so for this part, let's focus first on the yellow group. So the logic function that we will arrive at is A, since A is equal to 1, B is unchanged, which is 1, and literal C changed from 1 to 0, as well as literals D and E changed from 1 to 0. Therefore, we will arrive at A, which is ANDed with B. So it it will become AB. So for the second one, the green group, okay, so A is 1, and then B changed from 0 to 1, therefore it is cancelled. C is unchanged, which is 1. D changed from 0 to 1, therefore it is cancelled. And E is unchanged because it is just 1 in this group, in this green group. Therefore, what we are left is A ANDed with C ANDed with E. So actually, the one that I entered here is already in factored form, knowing that A is common, in each of the terms. Since the given K-map is a 5-variable K-map. So for the blue group, lastly, A is 1, B changed from 0 to 1 and is cancelled, C is constant at 1, D is constant at 1, and E changes from 1 to 0. Therefore, what we are left is A ANDed with C ANDed with D. So combining these functions, we are arrived at A prime ANDed with A times the quantity B poured with CE and poured with CD. So applying the simplification theorem, this A will be cancelled. Therefore, what we are left here is a simpler logic function for the output C, which is A prime or B poured with CE poured with CD. So this is the logic function for output C. So moving on with the next output, let me just clear my drawings. For output B, so this is the K-map that I did for output B. So for output B, here is the groupings that I made. So first one, for a while. Okay, so here is the first group. Second group, and this is the third group in yellow. So for the fourth group, it is this one, and the last group is this one. So focusing on the red group in this part of the K-map, so it will become A is 0, B is unchanged, which is 0, C changes from 0 to 1 and is cancelled, D and E literals are cancelled because they changed bits. Therefore, we are left here by A prime ANDed with B prime because A and B are both 0 and are unchanged. For the orange group, A is 0, B changed from 0 to 1, C is unchanged, which is 0, D is unchanged, which is 0, and E changes from 0 to 1. Therefore, what we are left is A prime ANDed with C prime ANDed with D prime. So for the yellow group, A is 0, B changes from 0 to 1 and is cancelled, C is unchanged and is 0, D is unchanged, which is 1, and E is unchanged, which is 0, because the ones here on the yellow group lies on the same column. Therefore, we are left by A prime, ANDed with C prime, ANDed with D, ANDed with E prime. So here is the factored form of the expression where A is equal to 0. So on the other hand, if A is equal to 1, focusing first on the green group, here's the green group, A is 1, B is unchanged, which is 0, C is changed from 0 to 1, therefore it is cancelled, B and E are also changed, therefore they are both cancelled. Therefore, we will left with A. We will be left with A ANDed with B prime. Last group, which is the blue group, A is 1, B changed from 0 to 1, C is unchanged, which is 0. Therefore, D and E are also changed. Therefore, we are left with A ANDed with C prime. Therefore, for this part, so the logic function rather that will be formed is A ANDed with B prime or A ANDed with C prime. So here it is in factored form. So combining this, we will arrive at this one. Let us take note that here is A prime and B prime. Here is A ANDed with B prime. So simplifying this, we will just arrive at B prime because A prime ANDed with A will yield a value of 1. Therefore, it will just become B prime, which is ORed with this one, ORed with this one. Applying the simplification theorem once again, we can remove this A prime in order to provide a much simpler output for D, for output D. Therefore, the logic function will become B prime or C prime B prime or C prime E prime or A C prime. So next one, so moving on with the output E. So here is output E. So here are the groupings that I made. So first one is this group. This group. And the second group is this one. And this one. So for the second half of the K-map, so the third group is for output E is this one. And the last group is this one. So focusing on this part of the K-map where literal A is 0, so focusing on the red group, A is 0, B is unchanged, which is 0, C is changed, therefore cancelled, literals D and E are changed, therefore cancelled. Therefore, it will become A ANDed with B prime. Focusing on the orange group, A is 0, B changes from 0 to 1 and is cancelled, C is constant, which is 0, literals D and E are changed, therefore they are cancelled. Therefore, it will become A. It will become A ANDed with C. Wait. Just a correction. So here are the groupings that we made. So first group, second group, and this is third group. So I had a mistake, so sorry for that. So next group is this one, while the last group is this one. So for the logic function, if A is equal to 0, so focusing on the red group, A is 0, B is 0, C, D, and E changes, therefore they are cancelled. Therefore, it will become A prime ANDed with B prime. Focusing on the orange group, A is 0, B is unchanged, it is 1, C is also unchanged, which is 0, and then D is unchanged, which is 0, E changes from 0 to 1, which is cancelled, therefore, we will have A prime, C prime, B prime. Okay, the next one is the yellow group. It will become A is equal to 0, therefore this is A prime, then ANDed with B, ANDed with C prime, ANDed with D, ANDed with E prime. So it will become like this: A prime, C prime, D, and E prime. So here is the factored form of this function. When A is equal to 1, on the other hand, so in the focusing on the green group, this is the green group, so A is constant at 1, B is unchanged, therefore this is 0, or B prime, C is unchanged, it is 0, or C prime, D and E changed, therefore we are left here with A ANDed with B prime, ANDed with C prime. So for the blue group, A is 1, therefore it will become A, B is unchanged, which is 0, therefore it will become B prime. C, a literal C is changed from 0 to 1, therefore it is cancelled. D and E are both 0 because they both, these cells lie on the same column. Therefore, it will become A and B prime and B prime and E prime. So here is the factored form of this Boolean expression. For the output E, so distributing each of the combined factored expressions, here is the output, the logic function for output E, which is A prime B prime, or B prime C prime, or A prime C prime B prime, or A prime C prime E prime, or B prime D prime and E prime. So moving on with output F. So where is output F? So here is the grouping that I made for here is the first group, And then the second group. And this is the third group. And this is the fourth group in this K-map. So if A is equal to 0, focusing on the red group, A is 0, B is unchanged, it is 0, literal C, D, and E are changed. Therefore, we are left here with A prime ANDed with B prime. For the orange group, A is 0, B is changed from 0 to 1, therefore is cancelled. C is unchanged, it's 0. D is unchanged, it is 0 also. While E is changed from 0 to 1, therefore E will cancel. Therefore, we will be left here with A prime ANDed with C prime ANDed with D prime. So that is for the orange group. For the yellow group, A is 0, B is changed from 0 to 1, therefore cancelled. C is unchanged from 0, which is 0. Since these ones in the yellow group lie in the same column, D will become 1 and then E will be 0. Therefore, the expression will become A prime ANDed with C prime D E prime. So that is for the yellow group. For the green group, for this row, A is 1, B is 1, C is 1. Since this group lies in a single row, and D and E will cancel because they changed, the values are changed. Therefore, we will be left with A ANDed with B ANDed with C. Combining these two functions, we will arrive at the function for output F, which is this one. So applying again the simplification theorem, the logic function for output F will become A prime B prime ORed with A prime C prime D prime, which is ORed again with A prime C prime E prime, ORed with A B C. So that is the logic function for the output F. And then moving on to the last output, which is output G. So this is the K-map for the output G. So let me draw again. Where's the pen? Okay. So based on the first K-map, all of the cells in this part of the K-map where A is equal to 0, they are all 0. Therefore, it follows that if A is equal to 0, the following logic function that we can make in SOP is just 0, because it indicates that all of the cells in this part of the K-map, they are all 0. So for this part, they are all 1. So we can group them into a single group, which is for the entire K-map. So it will be like this. The grouping will be like this. So based on the grouping, A is equal to 1, literal B changes and therefore cancelled, as well as literal C, D, and E. So those 4 literals will be cancelled. So we will be left with A if A is equal to 1. Therefore, combining these two logic functions, 0 and A, the output will be the sum. Applying the identity rule, the function for output G will just be simply A. So that's all regarding the K-map as well as the analysis for the truth table.
So now let's implement our the decoder from this canonical form from this K-map. So I already put here 5 inputs from A to E. So first, to be organized, let's put 7404 here. Okay, second, we need to connect the ANDed inputs. So the two inputs that are ANDed, for example, this C naught and D naught. So connect it, C naught and then D naught, and should be labeled B. C naught and D naught. And then C naught and E naught. This is our E naught here, and then label, and that's an E naught. Label. Next is A and C. So now that we're done with the two inputs that are ANDed, let's now do this three inputs that are ANDed. So we already have A naught and AC naught. So let's add another 7408 here, and then maybe here. So AC is ANDed with D naught. D naught is this D naught. Okay, D naught is here, and the output should be A naught and C naught and D naught. So let's copy. Okay. Next, this input again, but it is ANDed with E naught. So now, all we need to do is connect these wires here to our 7432 IC or the OR gates. So So let's start with output A. So it says here in this canonical form that B naught is B naught, okay, B naught or C naught and D naught. And this, and then C naught and E naught. This one. Oops, I need to be very careful. And this, or A and C. So the output of this, the output of this is our output A. Here, output A, small letter A. And then for B, A not connected to A, to R or A. The output of this is B. Okay. Next, for output C, so it says here that A naught, which is this wire, A naught is A naught or B. This is the output C. Small letter C. And then for output D, B naught. So we have here our B naught. Just connect this B naught and here B naught or C and D. The output of this is output D. Now let's proceed to output E. So A and B is or A and B or B and C. And the output of this is output E. Output E. Next is output F. So we have this and then this. The output of this is our input F. Input F, and then for our G, it is simply A. So let's put an output here labeled as G, small letter G, and then let's connect this A wire to here. So we're done with our decoder. So now let's see if this decoder satisfies this truth table. So this is our guide. So from 0 to 10, the display is 0. From 11 to 15, it should be 1. From 16 to 22. From 21 to 27, 3. And from 28 to 32, 4. So let's see here, 0, 0, 0, 0, 0, 0. The display is 0. So let's test for 10. 0, 1. 0, 1, 0, it's still 0. So for 11 to 15, the display should be 1. So let's test 01, 011, it's 1. And for 15, 0111 is still 1. So now from 16 to 20, the display should be 2. So let's test. So 1, 0, 0, 0, 0, the display is already 2. And for 20, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, the display is 2. And from 21 to 27, the display should be 3. So let's test. Let's see if it's the same. So 1, 0, 1, 0, 1. Now it's 3. And for 27, 1, 1, 0, 1, 1. 1, 1, 0, 1, 1. It's still 3. So now let's see if 28 to 31 is 4. The display should be 4. Now let's test. For number 28, 1, 1, 1, 0, 0, 1, 1, 1, 1. Now it's 4. So for 31, 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1. So now we can conclude that this decoder satisfies this truth table. Thus, it can be used for our system.
Good day everyone. For this project, I am tasked to do the comparator, the adder, the 5-bit incrementer, and to create the final circuit. We already made the comparator in our lab 3 and my group mate was assigned to it. So here is our simple comparator wherein we have 2 inputs, A and B, and we have 3 outputs for the low, high, and equal. So here is the condition. If A is less than B, output is not A ANDed with B. And if A is greater than B, output is A ANDed with not B. And if A is equal to B, output will be not A ANDed with not B, or with A and B. And for the adder, this was assigned to me in our laboratory activity 3, and I also used this in laboratory activity 4. So here, as you here for the sum, the SOP is A XOR B XOR C. So I use 7486 IC here, and as you can see, there are 3 inputs here, 2 outputs, which is the sum and the carry. For the carry, it is C ANDed with A XOR B here, or with A and B. So here is the circuit for the full adder. For the decoder, it was already discussed by Mamales, Emerlyn Jade. So here it is. And for the 5-bit incrementer, I use the adder. Here it is the adder connected to the ground. And as you can see, there are 10 inputs, A0 to A4, and B0 to B4. And we have 5 outputs, S0 to S4. For the full adder, or for the 5-bit incrementer, the carry in is connected here. So the carry out of the first adder is connected to the carry in. Same for the second adder, third adder, fourth, and for the last adder. So for our final circuit, we will be needing 2 sensors, so let's label this as sensor 1, and this one as sensor 2. We will be also needing the threshold. So I will be connecting this to the comparator. And as stated in the problem, the sensor should be equal or greater than. So we will be using the high and the equal. And this will be ORed, so let us use 7432. This will be ORed. And these two outputs will be ANDed. So let us use 7408. And this will be connected to our 5-bit incrementer. other inputs are connected to the ground. And let us put 5 inputs here. And connect them. And their output, let's label this as the comparator. Better. Let's try to change it. 8 maybe. Some more paper. Okay, let's use 8. And here let's try. Other. Other, and let us now use the decoder. And let us put the 7-second display here. And there we have it, the final circuit for the project 1. So let us test our circuit. So if threshold is greater than the sensor, so 1 to 10, so 0 to 10 is 0, and 11 is 1, 11 to 15 is 1, and 16 is 2, up to 20. So 20 is 1 0 1 0 1, so 3. Wait. No, sorry. So 20 is 1 0 1 0 0, so 2. So 1 0 1 0 1 plus 21, so 3, up to 27. And for the next one is 28 up to 31. So as stated in the problem, if the sensor is equal or greater than the threshold, it will increment 1. So for example here, 10, it will be 1. Let's try if the sensor is greater than, it will increment 1. And for 16, let's try 20. So let's try 20. 1 0 1 0 0. So instead of 2, it will increment if the sensor and threshold are equal or greater than. And let's try 27. So 27 is 1 1 0 1 1. Instead of 3, it will increment to 4. And that's all. Thank you. And here is the final circuit for our project 1.